Hello everyone. In this presentation I will talk about a multirate approach to event-triggered control of periodic autonomous systems. So let's start with a brief introduction to event-triggered control. So in traditional time-triggered sample data systems, the sensing, control, and actuation are all driven by clock, whereas in event-triggered control, the information are exchanged when it is necessary, and this necessity is decided based on a triggering condition. As opposed to time-triggered control, the event-triggered control results in a periodic sampling instance, which makes the design and analysis of such systems more complicated. However, the systems are efficient in terms of using communication resources. So here you can see a description of the problem. So the plant is a linear discrete time system whose parameters A and B are periodically varying. Therefore, we design a periodic linear controller to stabilize the system. And also there exists an event triggering mechanism between the controller and the plant. We also follow the following notation to refer to the index J by the pair K and G. And also we define the following order on this pair K and I. To design the event triggering rule, we first transform the system into a higher dimensional space using lifting technique. Doing so leaves us with a LTI system rather than a periodic one. The discrete time lifting operator stacks the elements of some signal B to form a higher dimensional vector V tilde, and it is not difficult to verify the following properties for the lifting operator L, which defines an input-output relation between the two vectors. So as you can see, the L is a non-causal and time-varying operator, and both L and its inverse preserves the L2 norm. Using the lifting method, we transform the system into the following one, which is linear, and hence we can design the triggering condition using the linear tools. We also impose the following set of standard assumptions on the stability matrices, and as a result conclude that under these assumptions the event-based model is asymptotically stable, and also it has a ripple-free closed-loop response. Next, we move to a more interesting scenario in which the lifting technique is used not only for the analysis but also for the design of the event triggering law. Compared to the previous scenario, the communication channel here is placed before the controller, and also much less computational efforts are required to decide the triggering instance, and as the triggering instance are checked with a period of Q. Also, this requires a higher bandwidth for the communications, since the signal to be communicated is of higher dimension. Also, in this scenario, we solve the issue of trivial triggerings, which happens when two consecutive triggerings occur. So here you can see that the lifted model for the second scenario, as well as the design triggering condition. So you can see that the controller and also the triggering condition in this case are designed based on the lifted signal rather than the original one. So again, we consider a set of assumptions on the stability matrices, but this time the assumptions are made on the lifted domain rather than the original one. So under these assumptions, we can show that the model is asymptotically stable and it has a ripple-free response. Moreover, we can show that the obtained set of triggering instance follows the non-triviality property. We conclude with the three main points. So using the lifting method, the triggering design for linear periodic systems can be performed using the linear tools. Also, we showed that the lifting theories can be used not only for the analysis but also for the design purposes. And finally, we have shown that the proposed lifted based event trigger law guarantee a non-trivial triggering instance. So thank you for your patience.